Okay, this is an explanation of Apollonius Conics, Book 3, Proposition 45. And I think I understand this, but I'm sure there's a lot more to learn, so try and follow along and see if you can understand it as well. So Proposition 45 is what we have out here. We're dealing with a hyperbola, an ellipse, also a circumference of a circle. So he says, if in a hyperbola or ellipse or circumference of a circle or opposite sections, straight lines are drawn from the vertex of the axis at right angles. The axis is this green line here, and you can see some of the straight lines that have been drawn from that. And a rectangle equal to the fourth part of the figure is applied to the axis on each side, and exceeding by a square figure in the case of the hyperbola and opposite sections, but deficient in the case of the ellipse, and some straight line is drawn tangent to the section and meeting the perpendicular straight lines, then the straight lines drawn from the points of meeting to the points produced by the application make right angles at the aforesaid points. So he has these two pictures for this one, the hyperbola and the ellipse. And he talks about exceeding and deficient, and that's going to apply to these shapes in particular as we go along. So he says, let there be one of the sections mentioned whose axis is AB. AB is here, this green line. AB is here, this green line. And AC and BD are at right angles. So this angle is right, this angle is right, this angle is right, and this angle is right. And CED tangent. So we have that tangent line here and that tangent line there. And let the rectangle AFFB, so AFFB, so this rectangle on the green line here, and the rectangle AGGB, which is the exact opposite, AGGB, still that rectangle on the green line, equal to the fourth part of the figure, be applied on each side, as has been said, and let CF, CG, DF, and DG be joined. So we have our axis as AB, the green line. AC is a right angle, BD is a right angle, CED is our tangent. And then he says rectangle AFFB, that rectangle on the green line, is equal, and he says to the fourth part of the figure. And I find that very confusing, and he does not explain that very well. So the way that I have written that is a 1/4 part of AB. And I should specify that the square on AB. And rectangle AGGB, which is the exact same rectangle essentially on the green line, is also equal to a fourth part of the square on AB. So if we were to draw a square on AB, then this rectangle is a fourth of that square. I think that's what he's saying, but like I said, he does not define it that well. So that will be explained. And he uses Euclid, Book 6, Propositions 28 and 29 to describe this, which says that we could create a parallelogram that is equal to sort of a random rectilineal figure, and also there's proportionalities there as well. But 28 specifically talks about exceeding, and 29 talks about deficiencies, which is what was mentioned earlier in our proposition, which we'll kind of get to. So first of all, he says, I say that angle CFD, so this angle right here, and angle CGD, so this angle right here, are right. That's what he's trying to prove. But before we get to that, we need to talk about the exceeding and the deficiency a little bit. And that has to do with the fourth part as well, which he talks about. So, Apollonius is very unclear about some things, and he's not very thorough, as we have already noticed. He talks about what is now today called foci, I believe. He never uses that word, but I think that's what it's called today. I think what he calls it, or maybe what it was called back then, is the points of application. So it's the same thing as foci. And what are the points of application? They are the points that lie on the axis line. So the axis line is AB here. So this green line in both of these, so this is the hyperbola, this is the ellipse. The green line in both of these would be the axis line. And the points of application are F and G on both of these axis lines. So those are the points of application, or foci. And the website that we've been using to explain Apollonius a little bit better has this sort of equation. So the rectangle AFFB, so this rectangle here, is equal to AGGB. So AGGB, this rectangle over here, which is exactly what we have in our propositions here with those two rectangles on the green line, is equal to a fourth part of the square on AB. So that rectangle here is equal to a fourth part of this square on AB. And that's exactly what we've seen in our other proposition, and that is points of application, I think is what that's called. But here's what's interesting about this. In this hyperbola, you can see that the points of application they exceed the square. So exceeding by a square figure, points of application on the outside of that square. And in an ellipse, they are deficient. So they're on the inside. Deficient by a square figure, points of application are on the inside of the ellipse. And if we go to our other picture, and probably write this down as part of your definitions, I don't know if it will come up later, but it might. We can see that over here. So in our hyperbola, you can see the points of application are underlined in pink, and the axis is the green line. So in a hyperbola, our points of application are on the outside of our square here, and in the ellipse, they are on the inside. And if we were to expand, if we go back to here, if we were to expand these points of application in an ellipse, the ellipse would also have to expand. So it has to be that way with the ellipse, and it has to be this way for the hyperbola, which he mentions in his earlier definition. So as part of his proposition, he says, and exceeding by a square figure in the case of the hyperbola in opposite sections, but deficient in the case of the ellipse. So he's already basically laid that out, that that's the way that it has to be. And Euclid's propositions also talked about that as well, exceeding and deficient. There's just certain rules to those things. So, back to his proof. He's going to prove that these two angles are right. So, let's get into it. So rectangle ACBD.